Okay, so the next few sections are going to be all about constructing various geometric quantities using the definite integral. And we're going to start by looking at areas of irregular shapes, in particular, the areas of regions that are bounded by the graphs of functions. So what we're calling curves here. So, recall the definition of the definite integral. Really, what I want you to focus on is that a definite integral is really just a sum of products. It is a sum of all of these tiny little products where delta x is a small quantity. And then you take the limit of this whole thing as this small quantity gets indefinitely smaller. So that's really what an integral is. So we have already seen that if f represents velocity and x is in units of time, then what does this do to here? Well, if this is velocity, then that's, say, meters per second. If this is time, then that's, say, seconds. So meters per second times second, well, that gives you meters. So velocity times distance is velocity times time is a distance measurement. So what you're doing is you're adding up a whole bunch of little distances. And ultimately, that's what the definite integral gives you. It gives you a distance. But of course, the situation isn't unique to measuring velocities and distances. Really, the physical significance of this quantity just depends on the units of what you're feeding into it. Right? If f and delta x had different units, then this definite integral would also have different units. The unifying principle isn't literally what we're measuring. The unifying principle is the fact that this is some quantity that has been built up from little products. And of course, there's tons of things that we can construct in a similar fashion. So that's what I try to summarize in what I'm just calling a general principle, an organizing principle that is going to motivate this section and the next few sections. A definite integral can be used to compute any quantity which can be constructed by summing up little products of this form. So when I write dx here, formally it's just a symbol. It's part of the notation for writing down a definite integral. By itself, it doesn't actually mean anything. But let's ascribe to it the meaning of what we're going to call an infinitesimal. Namely, when we see a quantity dx, or anything with a d in front of it, that's going to represent an arbitrarily small, but still non-zero quantity with the same units as x. So if x represents time, for instance, then dx would be a very, very short interval of time. If x represents some length on the x-axis, then dx represents a very, very small sliver of length along the x-axis, right? It is whatever the units of x are, but made very small. And definite integrals are just taking things like this and adding them up. Okay, so as a matter of notation, if I write something like this, just f of x, without any additional context, or g of t, or h of s, right, like the symbols don't really matter, what I'm referring to is an abstract function. Just an arbitrary rule for taking an input and returning an output. The rule may be written with a formula, Like, for example, f of x could be x squared, or it could be sine x. There might be a formula for it in terms of elementary functions, but that's not necessary. Really, it's just an arbitrary rule for associating inputs and outputs. There doesn't have to be a formula associated with it. Now, by contrast, if I write something like y equals f of x, if I write an equation like this, what I very specifically mean is the graph of the function f of x in the xy plane. So, a geometric object. F of x by itself is an abstract object. Y equals f of x is a geometric object. So, it's a curve in the xy plane. It is literally the set of points xy where the y-coordinate and the x-coordinate satisfy this equation. If we have the coordinates written the other way around, so instead of y equals f of x, we have, say, x is equal to a function of y, that's the same interpretation. This is a curve in space, or a curve in the plane. So let me just remind you that the graph y equals f of x, that has to pass the vertical line test. So the graph of y equals f of x, if you draw a vertical line, it's going to intersect the graph no more than once. Whereas, if the roles of the two coordinates are interchanged, so if it's x is a function of y, then this is going to be a graph that passes the horizontal line test. So any horizontal line is going to pass the graph no more than once. So basically, x equals f of y, y equals f of x, it's the same situation geometrically, just reflected about the 45-degree line. You're literally just switching the roles of the x and y coordinates. So geometrically, it's like you're just reflecting everything. So y equals x squared might be a vertical parabola, whereas x equals y squared would be a horizontal parabola. And I bring that up because, we're going to be seeing equations of the form x equals a function of y pretty frequently in the next couple sections. So we need to get comfortable with thinking of equations of both styles. Okay, so suppose we have two functions, and one of them is larger than the other. Then, if we look at the graph of y equals f of x, so f is the larger one, that's going to be above the graph of y equals g of x. So one curve higher than the other curve, for all values of x inside some prescribed interval. Therefore, we can consider the region that is bounded on top by one of the graphs, bounded on bottom by another one, on the left by a vertical line, and on the right by another vertical line. How can we find the area of a shape like this? So this is literally the area between the graphs of two functions. Now, as always, we should start with the simplest case, and then try to make it more complicated from there. Well, the simplest case would be if the two functions are constant. If a function is constant, then its graph is just a horizontal line. Consequently, you would have horizontal lines on top and bottom, vertical lines on left and right. It's a rectangle. So its area is literally just length times width. It's the product of the two dimensions. So length along the y-axis times length along the x-axis. What is the length along the y-axis? Well, that is the difference between the two functions, because f is on top, g is on bottom, so their difference is the distance between them. Similarly, the length along the x-axis is b minus a, right? If we have a on the left, b on the right, then b minus a is their difference. That is literally the distance between them. So that's the simplest case, if the functions f and g are constant. Now, of course, let's suppose that they are not constant. our strategy our strategy is going to be to take this region and slice it into a bunch of little rectangles, and then add up the areas of all those little rectangles. And when I say add up, in this case, I mean take an integral. So slice this region along a vertical line, and don't worry because we're going to do examples of this. Slice the region along a vertical line which intersects the interval that we're interested in at some value of x, say x star. So if you just slice a vertical region, just intersect it with a vertical line, technically speaking, that's infinitely thin, but we can imagine that the slice has some sort of thickness, like the thickness of a pixel. If we were looking at a drawing of it, the thickness of your pencil tip. And let's call that delta x. That is the thickness of the slice. Now, one of the unifying principles of calculus is that we assume that the functions f and g are approximately constant provided you restrict your attention to a small enough subinterval. And delta x, namely the width of the slice, is exactly as small as we need it to be, right? If it's not as small as we need it to be, just imagine that it's smaller. So, we're going to say that the functions f and g are constant where they intersect with the vertical slice, right? We slice this region, and the place where we slice it is so thin that the functions f and g are constant on that slice, effectively. So, we can imagine then that the slice is in fact a very thin rectangle of width delta x that intersects the graph y equals f of x on the top and intersects the graph y equals g of x on the bottom. Consequently, the area of this rectangle is, well, same as what we had before. It is the length along the y-axis, which is the difference of the functions, because f is on top and g is on bottom, times the thickness. We can then obtain the area of the whole region by adding up the areas of every possible vertical slice. One slice for every value of x in the interval that we're focusing on. Now, of course, since each slice is infinitely thin, there are infinitely many slices that we could do. So what we would actually end up getting if we tried doing this, like say with a pencil, is a Riemann sum. But let's just imagine that delta x is smaller than what we started with, and then do it again. Then imagine that delta x is even smaller, and do it again. Well, what are we doing? Oh, we're literally just taking a limit of Riemann sums. Yeah? So morally, this idea of adding up slices, even though each slice has a finite thickness, because we can imagine it to be as thin as we want, adding up all of those slices is morally equivalent to taking a limit of Riemann sums, whereby we obtain a definite integral. So this f minus g becomes f minus g in the integrand. Delta x transforms into the infinitesimal, because this represents the thickness of a slice, which is infinitely thin. And what was I saying before? Infinitesimals represent really, 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 really thin bits. So it really is as if we are just adding up the areas of a bunch of little rectangles, where the height of the rectangle is f minus g, and the length of the rectangle is the thickness dx, which is some very, very small thickness. Suffice to say, if you don't care about where this formula comes from, although I do think it's necessary to understand why we're interested in integrals in the first place, is that integrals encode this whole summation procedure. If all you're interested in is the area between these two curves, all you have to remember is that it's the integral of top minus bottom. That's really all you have to remember. So if you can draw a sketch of the two curves, and you can see which one is the top, which one is the bottom, then there you go. That's your integral. Yeah, and this is basically what I've already said. The argument above can be summarized with infinitesimals. Slice the region into thin rectangles of length dx. Their height is necessarily going to be the difference of the functions, because f is on top and g is on bottom. Therefore, the areas, so dA, so the area of a little slice is, well, height times thickness. And then you just add all of these up, where adding, in this case, is played by the integration operation. Okay, let's do some examples then. So let's start by finding the area of the region bounded above by y equals x squared plus 1, bounded below by y equals x, bounded on the sides by the vertical lines x equals 0 and x equals 1. So of course, what we have to do here is we have to start by getting a sketch. Now I'm going to use GeoGebra. So there we go. So we've switched over to GeoGebra now. So let's see. One of them was y equals x squared plus 1. So we can literally just type that in as shown. And there you go. So x squared is a parabola. Plus 1 means that it's just been lifted by 1 unit. So we have a parabola. See, if we just look at x squared by itself passes through the origin. So x squared plus 1 is just lifted by 1 unit. By the way, now would be a good time to look up the graphs of elementary functions, because when you take the exam, right now the plan is still for the exams to be in person. So you're not going to be able to... Are you allowed to use your calculators? Oh boy. I would have to ask my superiors if they want you using graphing calculators on the exam. I would be fine with it. So if you have graphing calculators, I would be fine with you bringing those into the exam, in which case you wouldn't have to worry too much about the sketch, because you could just use your calculator. But I really should ask my superiors about that, because it's been the case in the past where they're like, students can't bring in graphing calculators. That's cheating, which, I don't know. I mean, look at what we're doing anyway. We're all in front of computers anyway, so I'm not morally opposed to it. Anyway, just, yeah, your exams are going to be in person, so be aware that you may need to draw a sketch by hand. You can't necessarily rely on GeoGebra. But while we're here, what have we got? So y equals x squared plus 1, bounded below by y equals x. So y equals x is just the 45-degree line. Bounded on the left by x equals 0. So x equals 0 is literally just the y-axis. It is the vertical line that passes through x equals 0. And it is bounded on the right by x equals 1. Okay, so parabola on top, line on the bottom, vertical lines on the left and right. So this is the region that we're interested in. This region right here. So just to show you what I mean by all this vertical slice business, here, let me do this. Let me do things a little bit differently. Because really, all that we're interested in is the bit of the curve that lies between these two vertical lines, right? We don't actually need the whole parabola. So you know what we can do? Let's get rid of this, and instead, let's type f of x equals x squared plus 1. Right? So that's the same. All I've done now is I've written it in function notation. And then what we can do is to isolate the bits of it that are between x equals 0 and x equals 1. We can type function and then f 0, 1, like so. So now this red bit is really the only bit that we're interested in. And GeoGebra like names these things automatically for the most part. You can change the name later if you want, but right now it named it H. So now let's turn off F, and we can see there's the bit that we're interested in. And let's do a similar thing with the line. So let's say g of x equals x. Okay. Sorry, I got confused for a second. And then let's isolate the bits that are between 0 and 1. Okay, so now that's there in blue. GeoGebra decided to call it P. So now we can turn this off. You don't want to delete it because the G is still in the definition here. So if you delete it, then this is going to go away as well. But if you just click this button, that hides it. Okay, now to get a vertical slice, because the idea is we're cutting this into a bunch of vertical slices, segment. So segment gives a line segment between 2 points. So, oh, I'm sorry, before I do that, I need to start a slider. So if you just type S like this, what GeoGebra does is it automatically starts a slider. So now S is any number between -5 and 5. I want S to represent values of the x-axis though. So let's change that to go from 0 to 1. And let's give it a small step value, say 0.01. That way it's somewhat smooth. Okay, so here we have every number between 0 and 1. That corresponds to the values of x that we're interested in. Okay, now let me make a segment extending from S, comma, let's see. So the parabola is called H, so H of S, comma, S, comma, P of S. And now if we move the slider, we can see, there we go. So this is what I mean when I say that we take a region and then we cut it with a vertical slice. Now, mathematically, this is just a line segment, so it's infinitely thin. But of course, if it was infinitely thin, we wouldn't be able to see it. So it has a thickness, right? It's some number of pixels that is that it inhabits. So that is the thickness of this slice. That's dx. That is the infinitesimal dx. And then the area of this little slice is the integrand. That's the dude that we're integrating up. So we take the area of this slice plus the area of this slice plus this plus this plus this. You know, add up all of these areas. That is what the definite integral is doing. It is adding up the areas of all of these slices. And you can see, just looking at it, that all of these slices comprise the whole region that we're interested in. The region that we're interested in is literally just a union of all of these slices. So by adding up the areas of the slices, it is reasonable to expect that we should get the area of the whole region. Okay, so when it comes to the actual integral, though, we want to integrate top minus bottom. So the top is the parabola, and the bottom was the line. So now let's go back to Lix. That's the program I've been using to write the notes, by the way. It's called LYX, Lix. It has a bit of a steep learning curve. It's not very easy to get started, but once you learn all of the keyboard shortcuts, it's very easy to type math with it. Okay, so the top was the parabola and the bottom was the line. So the area is the integral. So the values of x are ranging from 0 to 1, so that's our limits. the top was the parabola, and the bottom was the line. So x squared plus 1, the parabola, minus x, the line. So it's top minus bottom. And let me put these in brackets to make it a little easier to look at. So there we go. So that's the integral that we need to evaluate. So let's see. So the parentheses really don't add anything of significance. So really, this is all we have. Although, I do like to put parentheses around the integrand because otherwise it just looks ugly. Now we need to anti-differentiate this, but that can be achieved just with the power rule. So let's see. X squared becomes x cubed over 3. The antiderivative of 1 is just x. The antiderivative of x becomes x squared over 2. And then we have to evaluate that between 0 and 1. The large thing really isn't any bigger, is it? Yeah, that kind of sucks. Anyway, when I write something like this, vertical line and then 1 and 0, that means I have to plug in 1, I have to plug in 0, and I have to take their difference. So that's a fundamental theorem of calculus. So let's see, if we plug in 1, we get 1/3 plus 1 minus 1/2. If we plug in 0, we get 0, so nothing else to be done there. So then finally, what is this? Let's see. So a little bit of fraction arithmetic. Bottom is going to be 6. 2 plus 6 minus 3. So what is that? That's 8 minus 3, so that's 5. So 5/6. Okay, so that's our final answer, 5/6. One second, let me open up the book next to me because I want to make absolutely sure that I'm not making any mistakes here. My lecture on numerical integration had some... I really messed up the Simpsons rule section, so I don't want to do that again. 5/6. Okay, we're good. Alright, next. Find the area of the region enclosed by these two parabolas. Well, once again, let's start with a sketch. Excuse me. Let's start with a sketch. So let's move over to GeoGebra. Let me get a fresh page. If you just reload, that'll clear it all out. So let's see. So y equals x squared. You know what? I'm going to write it in function notation, just in anticipation of, paring it down later on. And then what was the other one? 2x minus x squared. Like so. And we are interested in the area of the region between them. Okay. So the region between them looks like this thing. Now, you can tell from the graph that the intersections are at 0 and 1, but just to be pedantic, let's say that we didn't already know that we couldn't just tell from looking at the sketch, however you get the sketch, whether by computer or by hand. Let's say you don't actually know the x values where these guys intersect. Well, we can figure that out pretty easily. I mean, we need to know where these curves intersect because that's going to give us the lower and upper limits of the integral. And to find where they intersect, all we need to do is set the curves equal to each other. Set the right-hand sides in fact. So we get x squared equals 2x minus x squared, and then we can solve this equation. In particular, let me move everything over to the left-hand side. So 2x squared minus 2x equals 0. Then I can factor the left-hand side. Remember, if you have a quadratic equation, the way you solve it is by factoring, or by plugging it into the quadratic formula if you want. But in this case, the factorization is really simple. So either x is equal to 0, or x minus 1 is equal to 0, in which case we get x equals 1. So indeed, as we could see just by looking at the graph, they intersect. These two parabolas intersect at x equals 0 and x equals 1. So we already know that that's going to be... So we already know that that's going to be the lower and upper limits of our integral here. Now, we need to integrate top minus bottom. Well, let's see. Top is this red parabola. What was the red parabola? That was 2x minus x squared. And then bottom is x squared. So 2x minus x squared is the top. X squared is the bottom. So there we go. So there's the integral that we need to evaluate. And once again, this is a pretty easy one. I mean, it's just more practice with the power rule. So let's see. We can simplify this a little bit before we start anti-differentiating. Right? Because minus x squared gives us minus 2x squared. Now, anti-differentiate. So antiderivative of 2x becomes 2x squared over 2, so the 2's cancel. Antiderivative of this becomes 2/3 x cubed, right? Add 1 to the exponent to get 3, and then divide by 3. And now evaluate this between 0 and 1. So now it's just rote computation. If you plug in 1, we get 1 minus 2/3. If you plug in 0, we get 0, so nothing more to be done. So what is 1 minus 2/3? 3 minus 2 on the top. So what is 3 minus 2? That's 1. Okay, so 1/3 is our final answer there. Yep, and we are good. Next, find the area of the region bounded by the curves y equals sine x, y equals cosine x equals 0, and x equals pi over 2. Let me take this opportunity to remind you also to review your trigonometry. If, I mean, I know that that's a lot to review, but all you need to do is go to paulsonlinemathnotes.com. It was one of the links that I put in the first announcement, and just look at the trigonometry cheat sheet. And that has everything that you need to know about trigonometry for this course in it. So let's move back to GeoGebra and get a sketch. So sine x, cosine x, x equals 0, and x equals pi over 2. Let's get a fresh slate. Yeah, it's a good idea to put curves in function notation when you're doing it in GeoGebra because that way they have different labels that you can associate them with. If you just typed y equals sine x and y equals cosine x, then GeoGebra would just arbitrarily assign labels to it, And, well, it's better to just have more control over your variables. Okay, so we got our two curves here. We also need the vertical line at x equals 0. So that's just the y-axis. And we also need the vertical line at x equals pi over 2. So that is right there. So what is the region whose area we are trying to find? Well, let me turn off the background for a bit. What is the region whose area we're trying to find? Well, it is the region that is bounded by sine, cosine, and is in between these two vertical bars. So what is that? Well, it's actually two regions. So it's a bit of a trick question. It's this region here and this region here. Two regions. So notice in the first region, the top is cosine, the bottom is sine. In the second region, the top is sine, the bottom is cosine. So what we actually need to do here is write down two separate integrals and then add up their results. And the reason I took the axes away is because what I've seen people do in the past, because I used to have this as a homework problem, or something similar to it, is I saw people taking the area of this region here, bounded below by the x-axis, but that's incorrect, because nowhere in the actual question prompt does it mention that the x-axis is part of the is part of the bounds. So the x-axis isn't there. It's not actually real. It's just part of the coordinate system. However, the problem did state that x equals 0 and x equals pi over 2 do exist. So those are part of the problem prompt. This, however, is not. Okay. Now, we do need to know where they intersect. So let's see. Where do sine and cosine intersect? And this is where having your trigonometry cheat sheet on hand might be handy. So where do these curves intersect? Well, they're going to intersect at the value of x for which sine equals cosine. Do you remember where that is? Well, it's at pi over 4. Not too much to say about that. I mean, it's either you remember it or you don't. It's just at pi over 4, sine and cosine agree with each other. In fact, they agree with each other in infinitely many places. It's just pi over 4 is... Remember, we're restricting ourselves to values of x between 0 and pi over 2. So within this restrictive range, the only value of x where these guys agree with each other is pi over 4. And that's in agreement, roughly speaking, with what we saw in the sketch. Okay, so our area is composed of two pieces, as I was saying. So the first piece has cosine on top and sine on the bottom, and it goes from 0 to pi over 4. On the x-axis, mind, 0 to pi over 4. Oh my gosh. Butterfingers. Okay. And what was I saying? Cosine is on the top, sine is on the bottom. Okay. Like so. And then the second piece goes from pi over 4 up to pi over 2. And it's reversed. So in this case, sine was on top and cosine was on the bottom. Okay, so this is going to give us our answer. Okay, so just refer to the table of antiderivatives from the previous section if you need to, but you really should memorize the antiderivatives of the basic trig functions. In this case, antiderivative of cosine is sine. Antiderivative of sine is minus cosine, so minus minus becomes plus. And then that has to be evaluated between 0 and pi over 4. Antiderivative of, so let me put parentheses around this now. Antiderivative of sine is minus cosine, minus antiderivative of cosine is sine. So I'm being very careful about the negative signs here. From pi over 4 to pi over 2. Okay. So again, this is where having that trigonometry cheat sheet on hand. You know what? Hang on. Before I move on, let me take these two negatives and factor those out, because that's bothering me. There we go. That's much better. That may or may not make things easier, but I don't know. Little things like that get on my nerves. I want to minimize the number of negative signs in any particular expression. Okay. So if we plug in pi over 4, sine at pi over 4 is root 2 over 2. Cosine at pi over 4 is also root 2 over 2. Okay. If I plug in 0, sine at 0 is 0. Cosine at 0 is 1. Okay, so that's the first chunk. Minus. Let me put another big pair of parentheses here because this minus is making me nervous. So inside this parentheses, I'm going to put the entire second chunk. Okay, if I plug in pi over 2, cosine at pi over 2 is 0. Sine at pi over 2 is 1. Now if I plug in pi over 4, cosine at pi over 4 is root 2 over 2. And sine at pi over 4 is also root 2 over 2. Okie dokie. I know that's very ugly, but you have to be very precise with these sorts of things or else you're going to make mistakes. Let's see, so root 2 over 2 plus root 2 over 2 is just root 2. Minus 1 minus 1 plus root 2. So I'm taking this minus and I'm distributing it. So minus 1 plus root 2. So what do we end up with? So we end up with 2 root 2 minus 2. Okay. Let me double check that. Yeah, 2 root 2 minus 2. We're good. Okay. So, in these examples, we've been looking at curves that have been given by the form y equals f of x. So in other words, curves that pass the vertical line test. But of course, it needn't be like that. We could reverse the roles of the x and y coordinates, and all of our arguments would work out in exactly the same way, just with the roles of x and y reversed. However, if if our graphs pass the vertical line test, then we take vertical slices. And it's precisely because the graphs pass the vertical line test that taking vertical slices is sufficient to fill up the entire area. If it's the other way around, if we're looking at graphs of the form x equals f of y, then everything would pass the horizontal line test, so we would have to take horizontal slices instead in order to fill up the entire area. So it's the same situation, just reflected about the 45-degree line. So, whereas in this situation, it's integral top minus bottom, if we've been given x equals a function of y, then everything is right minus left instead, right? Same situation, just reflected a bit. So right minus left, that's really all you need to remember about this. So find the area enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. So before we do anything else, let's just rewrite these to be in the form x is a function of y. So for this one, just move 1 to the other side, so x is equal to y plus 1. And then for the other one, move 6 to the other side and then divide by 2. So x is equal to y squared minus 6 over 2, like so. Right, so now it's in the form x is equal to a function of y. Now, to be fair, it might be tempting to say, like, take the square root of both sides here so that you get y as a function of x, but you always have to be very careful when you're taking square roots, because if you take square roots of both sides of an equation, technically you have to add in a plus minus as well. And what that means is that you're actually getting two separate functions. So it's for that reason that taking square roots kind of makes me nauseous, and I want to avoid it wherever possible. So it's much better to just consider this whole situation to be in terms of x as a function of y, instead of trying to mold it in the other direction. Let's see. So what do these guys look like? So x equals y plus 1. So in GeoGebra, you can literally just type in x equals y plus 1, and it'll know what you're talking about. And then what was the other one? The other one was y squared minus 6 over 2. Oops. Put parentheses around this. All over 2, like so. And why is it confused? Oh, because it auto-corrected to f of x. Okay, there we go. Yeah, just type them in exactly as written. Okay. So, pretty clear that this is the region that we're interested in. That's the region we're trying to take the area of. Now we are integrating with respect to y, so that means the lower and upper limits of our integral have to be the smallest y value and the highest y value within this region, respectively, and that's going to be given by the places where these guys intersect. So let's see. We can tell from the graph that that's going to be from y equals negative 2 up to y equals 4. But we could do that algebraically as well. So by setting y plus 1 equal to all of that. So let's see. So we would get 2y plus 2 equals y squared minus 6. And let me move everything over to the right-hand side. So minus 2y, and then minus 2. Like so. And then we can factor this dude. Let's see here. How would this factor? How do you make 8? How do you make negative 8? It's 4 and 2. So minus 4 plus 2 will do it. Right? Because minus 4 times positive 2 is negative 8. Plus 2 minus 4 is negative 2. So that'll do it. So y equals 4 from this guy. And y equals negative 2. So indeed, that is in agreement with what we were looking at in the graph. Negative 2 up to positive 4. Everything is in terms of y now, so those are the limits of our integration. Okie dokie. So our area in this case, so we're going to take the integral from negative 2 up to 4 of right minus left. So looks like the line is on the left, or I'm sorry, the line is on the right and the parabola is on the left. So the line is y plus 1, and the parabola is y squared minus 6 over 2. And you know what? I'm just going to divide both of these guys by 2 to make it easier. Okay. So notice that because I'm subtracting this entire thing, I had to distribute the negative sign. So minus y squared over 2. But then minus a minus becomes plus. So plus 6 over 2, which is 3. So let's see, let's clean this up a little bit. So plus 1 plus 3 becomes plus 4. Oh my goodness. Like so. And now we can just hit it with the power rule. Two times 3 is 6. Oh my goodness. So the arithmetic on this one looks like it's going to be kind of nasty. So here's what I'm going to do. Let me plug it all in, but then I'm just going to do the computation off screen and let you know how it went. So if I plug in 4 squared is 16. 16 over 2 is 8. If I plug in here, 4 times 4 is 16. If I plug in 4 here, what's 4 cubed? Oh, that's 16 times 4, so that's 40 plus 24, so that's 64. And that's really the same as 32 over 3. Now if I plug in negative 2, so what happens if I plug in negative 2? So negative 2 squared becomes positive 4. 4 over 2 is 2. 4 times negative 2 is negative 8. Negative 2 cubed becomes negative 8, so negative negative becomes positive. And then 8 over 6 is the same as 4 over 3. Ugh. I was hoping that all the fractions would go away. Alas, that does not appear to be the case. Let's see. 3 times 8 is 24. Well, whatever. I'm just going to look at the book now. Um, 18. 18? Are you sure? One second. I wanna double check that. I know you've all stopped listening by now, so I'm really just doing this for my own satisfaction. So 8 plus, I have my calculator out now, 8 plus 16 minus 32 over 3 minus 2 minus 8 plus 4/3. Ah, it is 18. Alright, very cool. Okay, sorry this one went over 50 minutes. I really want these lectures to not last any longer than they would if we were in class, but, you know, you can skip through them as you please, so I don't think it's that big of a deal. Okay, so that's this section done. Basically, the takeaway is integrate top minus bottom, or integrate right minus left, depending on whether you're integrating with respect to x or y. Okay, thank you.